Hello, everybody. This is the video review of the study guide for exam 3. And just to let you know, I'm doing this while I'm also on Zoom. I'm not recording the Zoom at all, but um, to let you know, this is during a live session of Q&A, but nobody's here. So I'm trying to use this productively to go over some stuff that would be useful for you. And so I might be checking the Zoom once in a while. So just excuse that, but it shouldn't take too long to do that. So I'm just going to go bullet point by bullet point on the study guide. And so the first point on the study guide is the between subjects. And so between subjects, again, is each participant gets just one level of the variable, whether it's an IV or a PV. It's more likely an IV in this case. Um, so like the example that we've been using a lot in lectures is the color red, does it increase in traction? So let's say, so this is a ANOVA, we're in ANOVA territory, so it's got to be 3 or more levels. So we have red, green, and blue. So in a between subjects design, 1/3 of your participants get red, 1/3 get blue, 1/3 get green. And they rate the attraction of either the red or the blue or the green, the one that they see. And so they're only measured once on a dependent variable. Excuse me, I had to sneeze. They only get measured once on a dependent variable because they only see one color. They get measured once on the DV. And if you identify a study for this exam as between subjects, then you do a one-way ANOVA. And then relatedly, if you are identifying something as within subjects, you'll do a repeated measures ANOVA. So repeated measures, that should be a clue. Repeated measures is the multiple measures of a dependent variable. So if we have that same study, but we're doing it within subjects design, everybody's going to see red, green, and blue. So they're going to see red, they're going to rate red. They're going to see green, they're going to rate the green. They're going to see blue, they're going to rate the blue. So each person in that case is measured on the dependent variable of attraction 3 times. And so that's within subjects, and that's repeated measures ANOVA. I'm going to check my Zoom. Nobody's there. So I'm going to continue this. And remember that the repeated measures ANOVA, the only difference there is that we can identify those individual differences. So whether somebody's picky or not picky, or generally high, generally low, or generally in the middle on a dependent variable. And before I go on with this, just like our makeup exam, all the problems, so we'll have a conceptual part as usual, and then we'll have a problem part. The conceptual part, you need to have it be a closed book. This includes doing an ANOVA table, which probably comes down there a little bit more in the study guide. But that would include the ANOVA table stuff. So the ANOVA table fill-in is not considered to be a problem. It will be part of the conceptual stuff, is my take on it. And the only exception of that is I have to look at Canvas. So I don't know if Canvas will let you fill in the blanks, but I'll explore that. If it works in Canvas, it will be in the conceptual. If it doesn't work, it will be in a problem. But I think it's pretty easy. It's just adding things up, knowing that between subject plus within equals total. And then for the degrees of freedom, if you're giving the number of levels and how many people are in each group, if you have a one-way ANOVA, you can figure out the total sample size, and then you can get the degrees of freedom total. And if you know there's 3 groups, then you know the degrees of freedom for between is 3 minus 1, so that's 2. So then all you do is to figure out the within is to take the total minus the between, and you get the within. So again, obviously with these ANOVA problems, I'm not expecting you to memorize all of these formula. The problem part then obviously will be open book. I'm just checking nobody's there. Nobody's home, so I'll keep on going here. So just remember to be able to compute the effect size for both types of ANOVA. So eta squared for the one-way ANOVA and partial eta squared for the repeated measures. And it says interpret the mean of that statistic for both types. In the repeated measures, ANOVA, I didn't go over that much. I'm okay if you just interpret it as the percent of variance accounted for by the independent variable, or if it's a predictor variable. That's basically what it is. It's just like R squared with the RT test. So just like the R squared with RT test, you interpret it as the percent of variance accounted for in the DV from the IV, or if it's a PV, it doesn't really matter. So again, the percent of variance accounted for, percent of variance in the dependent variable accounted for in the, by the IV or DV. So make sure you can write the summary paragraphs for each of those types. So the form of that's been pretty simple. So you want to make reference to table 1, and you should be able to make those tables too. So be able to make a table 1 of the descriptives. It's just the mean and standard deviations for the levels of the variable, the IV or PV. And then and that's the mean and standard deviations. And so make sure you can do table 1. And make sure you do table 2, the summary tables. Make sure you can do a summary table for the problems. And so the summary paragraph starts off with reference to see table 1 for the descriptive, see table 2 for the ANOVA summary table. So that's the start of it. Then the next sentence is the statement about whether the variables relate based on the F test. So a color affects ratings of attraction. Then comma, you have the F, parentheses, you have the degrees of freedom for the between treatments, comma, then degrees of freedom for within if you're in the one way, or is the error for the repeated measures, end of parentheses, equals then your F that you calculated, and then comma, P is less than 0.05 if you rejected the HO, there's an effect. And then if they aren't related, then your sentence would be different. Your sentence would say, color does not affect ratings of attraction. Then you have your F, and then you would end it with NS, not significant. So if you fail to reject HO, it's not significant. And then we have here talks about that. Then we have a sentence. So if it's not significant, then we just stop because we're not supposed to dig into the post hocs. If it's not significant, you still report the effect size at the end, but you don't report anything about post hocs. So if it's significant, then you say that basically post hocs are needed to see which conditions or levels of the IV differ from each other. However, looking at table 1, the means and standard deviations, does it look like there's some differences between the groups or the conditions? And so you will have that sentence, that eyeballing stuff, if again your F is significant, you rejected HO. And then the final sentence for either one of these paragraphs is the effect size. And then we talked about the summary table. So obviously you'd be able to do that for the problems, but you also want to be able to, what was I going to say? You want to be able to fill out blanks in a partial summary table. So just like the one-way ANOVA homework, you should be able to do that. So you should be able to take the blank spaces and fill it out with the information that's given. So again, between plus within equals total. And then for the degrees of freedom, you might be given the levels of the IV. And for the summary table fill-in, we'll just have the one way because the repeated measure is a little bit more complicated. So the fill-in thing, just like the homework for one-way ANOVA, it would just be for the one-way, the between subjects. And so it will give you a number of levels, or it will say a number of groups. So let's say there's 3 groups of 20 people. So if there's 3 groups of 20 people, we know that there's 60 people in total in the study. So then you know that degrees of freedom total is 60 minus 1, it's 59. You also know there's three groups. So there's three for the K, the number of levels. So the degrees of freedom for between is 3 minus 1, so that's 2. So we can figure out within by taking total minus between, 59 minus 2, it's 57. So just know that you might have to figure out the degrees of freedom that way. And if you watch the homework video, you can see the solution for that little fill-in table in our homework. Okay, the next point on the study guide is understand the interpretation of the F statistic. What is it testing? So remember in the F, it's an overall test. So let's just take our example we've always been using, the red, green, blue. So it's not testing whether one color is greater than another color in terms of attraction. All it's simply doing is testing, is there some difference there? Is there some difference between those groups? Is there enough variance, if you remember the F, is there enough variance between the groups? They're so different. The groups are differing more than people just differ individually within a group. And so it's just telling us that there's some variation going on with the groups. The IV seems to be having an effect, but we don't know specifically what that effect is. So we're just testing overall, is there some difference going on? And we know that the F test, so the next little subpoint here, the F test is a protected test. And so it's protecting us against making too high of a type 1 error. So if we had the same situation, we have red, green, blue, and we said, well, let's just do a bunch of t-tests to see what the differences are. And you end up running 3 t-tests. Well, each of those 3 t-tests, we're going to have an alpha of 0.05. So you're going to end up having a 15% chance of making a type 1 error, and that's not good. That's not what we do. We want to do a 5% or below. And so the F tells us there's some difference, and then if there is a difference, if it's a significant F, then we can say, okay, let's go ahead and dig around the pieces because the F protects us from making the type 1 error. And you know that post-hocs also do that by dividing up the alpha, but the F is needed before we can dig into the pieces in the post-hocs. And then if it's not significant, so we fail to reject the HO, then it's saying there's really no differences between the groups, and stop, don't go digging, because if you're going to go digging, you could come up with a conclusion that's false, saying there's an effect there when there really isn't. So it's a protected test. So it's protecting us from making too high of a type 1 error, saying there is some effect when there really isn't. And we just talked about that right there. And so the post-hoc tests, we can only do them if the F is significant. We reject the HO. We can't do it if we fail to reject and say it's not significant, because what we just talked about. Why? Well, because of the type 1 error. Why are they necessary? Because the overall F just tells us there's some difference between the groups or the levels of the IV. It doesn't tell us which ones differ from each other. And basically, you interpret the post-hocs as comparisons. So it will, in our problems, and I think I'm not going to ask this conceptually, this would be in the problem. And so you would have to interpret these things in a way that you can interpret which things are different from the other. We're really just testing this on the lab. I'm not going to give you any SPSS output on the current exam. Maybe it might go in the final. So I'll just say how these are interpreted. Just I wouldn't worry about that too much. That's really more of a lab thing. Let me check if anybody's on. Nobody is, and I'll continue. And so we already talked about this a little bit. The F ratio conceptually represents the effect of the IV. So if you remember one way ANOVA, it's between over within. So the variance between groups, so the variance between the color groups, between red, green, and blue, how different are they on attraction? And then it's over the variance within. So if we take each group, so we take red and we say, well, if you're in a red group, you should be around the red mean, but people are not on the red mean. There's some variation there. So that's the variation within groups. So people are varying from their group, the red group. We don't know why they're varying. It's just that they're different from the mean. And so we just consider that to be error. We're making a prediction that they should be at the red mean, but they're not. So the difference between their score and the actual mean is called error, that little line. And so basically it's conceptually representing the effect of the IV. So the between variance is the effect of the IV. And then within is conceptually, they call it error, but you can think about it just how people vary. In the one-way ANOVA, it's just how people are varying. It's also conceptually what do we know versus what we don't know. And so the between, we know what's going on. There's something going on with the color. The within in the one-way ANOVA, we don't know exactly what's going on. There's some differences. We don't know what's going on. So it's conceptually also this thing that's in statistics, which is our stats are always sort of this ratio of what we know, what we can directly assign to our variables, IV, PV, in relationship to the effect on the DV, and then the leftover stuff, which we don't know why people are differing on the DV. And this is true also for the repeated measures. So if you remember repeated measures, the top is unchanged. It's still the effect of the IV. It's still the effect of color on attraction. And then on the bottom, what's different is that we have a smaller error. So it's not just within, it's within minus the between subjects to individual differences. And so then we have an error. So again, conceptually, it's what do we know, the differences between our treatment groups, and then what we don't know. So that ratio, basically, are we able to systematically assign, they call it, variance in the dependent variable to the IV versus what we don't know what's going on. And so using that example again is how much of the variance in attraction do we know is directly related to the colors of red, green, and blue? So that's on top. Then on the bottom of that ratio as well, there's differences here and we don't know why. So in the repeated measures, we've, obviously the top is the IV, the colors, the between treatments. And on the bottom, we've taken within minus the between subjects, because we know the between subjects. We know people are relatively high, people are relatively low. So we didn't have leftover errors, stuff that we don't know why people are varying. So conceptually, statistics are that ratio of what do we know is directly related to our variables in terms of the DV variance, and then the stuff that people are varying on the DV and we don't know exactly why they are. We haven't measured why they're different. There's not a variable that we can assign to that stuff, so it's unknown. It's a big question mark. And so I just talked about that second bullet point here. This one, what the F ratio actually means conceptually. And I just answered that last question. So all statistics are that ratio of what we know and don't know. Again, what we know is systematically we can say that this amount of variance in the dependent variable, let's say it's attraction, is directly related to the IV. In this case, it's the color. So we know exactly how much the IV has an effect. And then what's left over is on the bottom. People are varying and we don't know. So it's really that ratio of systematically we know for sure why people are varying. We have a system, we have numbers to tie the IV with the DV. And then there's a bunch of stuff that's left over in the DV variance that we're not sure why people vary. So that's all statistics. Let's continue. And so what is the F statistic likely to be significant? And so this is from your one-way ANOVA homework also. And so when the differences, the variance between groups or between treatments, so when the effect of the IV is higher than in the one-way ANOVA, it's the within, in the repeated measures, it's the error, the stuff that we don't know. So the effect of the IV is greater than the stuff that we don't know. And in one-way ANOVA, I'm okay if you answer this with a one-way ANOVA, because that's really from your homework, is in the one-way ANOVA, the between difference, the variance between, so between the groups, the color groups, red, green, blue, those groups are differing more than people differ within the groups themselves. So how people just naturally vary. And it's less likely to be significant when, that's the next bullet point, when our differences between the groups are not as large as there's differences within the groups. So the effect of the IV is smaller than how people just naturally vary. And that should make some sense because if we do our study and we create bigger differences with our IV, if color is making people act a lot more differently in terms of how they're attracted to people, compared to how much they just differ naturally in how they're attracted to people, then we can say, well, the IV did something more. We have evidence that the IV did something more than just is there in people in general, how people naturally vary on attraction. So then we can say, well, there's probably an effect here of our IV because we made a bigger difference. If the difference that we have between our groups is equal to or smaller, equal to, we'll just say, to the variance that's naturally there. So people just naturally vary from each other in terms of how attracted they are, let's say 1.5. So if we look at a group of people, not people differ in what they find attractive, et cetera. So let's say we found the standard deviation to be 1.5 between those people's attraction levels without doing any manipulation. Then we do a manipulation, we find our groups differ, red, green, blue differ by 1.5. Well, 1.5 over 1.5 is 1. We've done nothing. Our colors made absolutely no more difference than people just naturally differ. So in that case, it's not significant. And I'm going to go down here. And you can see that I think the study guide is pretty concise. And although it feels like there's a lot of stuff, really, it all boils down to being able to have a good notes for yourself to use for the problems. And then the conceptual things are pretty straightforward, I think. And they're not as immense, I think, or as voluminous, if I can say it right. There's not as many things, not as many points to learn as in previous tests. And so the only computational difference between one-way and repeated measures is that in the repeated measures, we can now identify the between subjects variance. So now we know how much people individually differ, whether somebody's higher in general, lower in general, or in between on the dependent variable. So in the attraction, we know if people are picky or not picky or average. And so here we can definitely identify it now in the repeated measures. We repeatedly measured the DV. We've measured attraction 3 times. So we now have a sense about in general, because we're not caring about the red versus green versus blue here. We're just saying in general. So you might go higher on red. Everybody might go higher on red, but your still relative placement is that there's some people still going to be higher. Some people go from 2 to 4 on red. Some people go from 8 to 10 on red. So there's a difference of 2. That's what we care about for the colors. But in this, the between subjects, we care that some people started at 8. Some people started at 2. And if that's a general thing across their ratings, then, well, some people are high, some people are low. And I just answered that last part. So we're able to do that extra thing because we measured the DV multiple times. And so the second to last question here is why repeated measures ANOVA has more power than one way. It's because the error is smaller. And so in the one-way ANOVA, we just divide up the total sum of squares, the total variance, into 2 pieces. There's the between and there's the within. So between is the differences between the groups, and whatever's left over is within the groups. And so the within is the bottom part, is the error in the one-way ANOVA. And that's relatively large, if you will. And then the repeated measures, because now we can identify the between subjects effect, how much people individually differ, high, low, medium in general on the DV, picky, not picky, average. We can then take that out of the within subjects. So the stuff now that we don't know within subjects in the one way, we now know another piece of that We know the between subjects, how people individually differ. Again, this is not the between stuff because between treatments is just simply the color group. This is on the bottom. On the bottom, we can take that old within, subtract the new stuff that we find out in repeated measures, the between subjects variance, the individual differences. And then now our bottom part of the F-test is smaller. The error is smaller. We've taken something out of the within that we now know, the between subject stuff, and now the error is smaller. So you can see that the top stays the same, the bottom gets smaller, therefore the F is bigger. You do know, though, from our practice problem in the repeated measures ANOVA lecture that it doesn't guarantee that you're going to find a significant finding because, like in that practice problem, we essentially didn't have much individual differences that were identifiable. People were all over the place on the test. I think it was a test with the sound. So people were all over the place. People were 8 or 2 or 3 and then 7. They were all over the place. There was no individual pattern there, and so our sum of squares between subjects was pretty small. So given that, we didn't actually reduce the within that much, and so in those conditions, then we didn't find things. But what we'd say is, well, we didn't find it, so really there's probably nothing there. And then this might be a little bit glib, but the last thing just says, know everything that was presented in the two-way or two-factor ANOVA. And so let me go to that lecture. For sure, the big thing is the interaction stuff. So you should be able to plot data and draw a graph like we went through. So we went through various things in the lecture. So we did go through some graphs that were given to you, and we went through the interpretation. And remember, there's one of two ways to interpret. You could interpret the lines, or you can interpret the dots. So if you're not quite sure what I'm talking about, go watch the end of the two-factor ANOVA video lecture, and it will tell you exactly what you should do. But then we had those exercises at the end. And so at the end of the video, we went through 4 examples where you were asked to draw the graph and then interpret the interaction. And so that's going to be a big thing that you should be able to do. And let me see if there's anything else. Well, basically, you should know what a two-factor ANOVA is. So two-factor is when you have 2 IV/PVs. And so unlike the one-way and the repeated measures, which is just one IV or PV related to the DV, two-factor is that you have 2 of those things, 2 IV/PVs, and then you relate that to the dependent variable. And the key thing is that we're finding 3 things. And so we have a main effect for the first factor. So let's say we have the attraction, the colors, red, green, blue, and then we have the social sexuality. I gave this example in the lecture. So how much people think about sex. And so we have an IV, the color. So we're going to test the main effect of the color. Does color itself, without thinking about the social sexuality, does color alone have an effect on attraction? That's a main effect. And then we have a main effect for social sexuality. So social sexuality, how much somebody thinks about sex alone without thinking about the color, does that social sexuality affect people's ratings on the attraction scores, the DV? But the big thing why we do a two-factor is the interaction. So does the color red interact with social sexuality to influence the attraction ratings? And so you don't need to know this. I said this in the lecture. And so then you basically need to be able to interpret. And I'm more curious that you interpret the interaction. So is there an interaction? And there's interactions when the slopes of the lines are different. So we have non-parallel lines. That indicates that there's interaction going on, that the two factors are playing with each other, interacting with each other on in terms of the effect on the DV. So crossover definitely has, and so basically, it's knowing what the two-factor ANOVA is. It's knowing what the main effects are and the interaction is, and then being able to interpret the data, including things like our exercises. So at the end, we went through those 4 exercises. So if you're given data, are you able to draw those things out and to interpret whether whether there's an interaction, and then second, to be able to put in words those interactions. And so again, if you want details about this, um, all through the lecture, I interpret the interactions that are already graphed in the lecture as we go through it. And then at the end, we have 4 examples, and I do the graphing. And I do the graphing in either approach because you can put one variable on the horizontal and one as lines. So I graph both approaches, one variable horizontal, one variable as lines, and I flip those variables. And I show you what they look like in case you take either approach, that's fine. And then for each of the graphs, each of those approaches, I go through the interpretation of the interaction, which you can interpret the lines or you can interpret the dots. So there's a very detailed thing in that video lecture. So I'm going to end this now. I'm just going to make sure that nobody's here, and I think I'm ending the meeting, which I probably will do anyway because nobody's here. And so that's the review of the study guide. So do attend the live sessions if you have any questions. But I think, although it seems like there was a lot of stuff at first with the one-way ANOVA, once you get down all of those steps, the conceptual stuff and the other things I think are pretty straightforward. And so I will talk to you